Welcome back. In this video, we're going to be covering some more integration techniques, specifically the integration technique of trig substitution. So to go ahead and get us started, let's refresh ourselves on our basic right triangle identities. So we're talking sine, cosine, tangent, and then all of the reciprocal trig functions. So to get started, let's create a right triangle with angle theta where cosine theta is equal to 3/5. We're going to draw a sketch and then find sine theta. So let's make sure to label our angle theta on our right triangle. There's theta. And then we're going to set up this triangle so that cosine of theta is 3/5. Now, probably many people have heard the SOHCAHTOA acronym. It seems to be pretty popular in a lot of high school curriculum. This little acronym helps us remember the legs of the triangle for sine, cosine, and tangent. So sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. So if cosine is 3/5, that means that the adjacent leg is 3 and the hypotenuse is 5. Now looking at the triangle this way, I can see that this triangle is a pretty common triangle, the 3, 4, 5 triangle, pretty notorious. Let's say that you didn't happen to remember about 3, 4 triangles. How could you find it? You could use the identity that a squared plus b squared equals c squared and find that 25 would then equal to 9 plus, and then b squared would have to be 16. So this would be 4. Okay, so now the last item, we need to find sine theta. So based on our triangle, sine theta would be equal to the opposite, 4 over hypotenuse 5. There we go. So hopefully this is bringing it back that once you have two sides of the triangle, you can always find the third side of the triangle using the Pythagorean identity. Okay, let's go ahead and do the same, but with cotangent of theta equal to x. Okay, so more variables involved here. Let's start by labeling our theta. So our theta is there, and then our cotangent of theta, well, it's the whole, and not really a number, it's a variable, but we can view it as a ratio by putting it over 1. So remembering that cotangent is equal to 1 over tangent, aka reciprocal. So if tangent is opposite over adjacent, then cotangent theta is equal to adjacent over opposite. Okay, so the adjacent leg must be x, and the opposite leg must be 1. And now we don't have our hypotenuse here, but that's okay, we can find it. So finding the hypotenuse, x squared plus 1 squared equals the hypotenuse squared. So then the hypotenuse must be the square root of x squared plus 1. Okay, now we need to find sine theta. So then sine theta, reading off our triangle, would be equal to opposite 1 over hypotenuse, square root of x squared plus 1. There we go. Okay, so hopefully this reminds you of those right triangle identities. Let's go ahead and see how this is going to apply to our integration. So as we have noticed, when we have a lot of radicals involved, we kind of struggle with integration, right? One strategy that is going to help us is our trig substitution strategy, specifically when we have radicals. Before we jump into our first example, let's go ahead and remind ourselves of the Pythagorean identities. We went over this in a previous video, but just in case you're coming here first for some reason, these are the Pythagorean identities. Cosine squared plus sine squared is equal to 1. 1 plus tangent squared is equal to secant squared, and that leads to the same identity, just kind of rewritten. Tangent squared equals secant squared minus 1. Those are going to be the trig identities that we use quite a bit. So for our first example, let's take a look at computing the integral of 4t cubed over the square root of 25 minus t squared. Okay, so when I take a look at this integral, my first instinct would be I really wish I could do a u substitution, and unfortunately with 25 minus t squared, I don't see, I basically have too much to make a u substitution because I don't see just t, I see t cubed outside the integral. So a u sub is not going to work here. However, maybe there's another way to do a substitution to make the radical easy. So this is not intuitive. This is the first time you're seeing this, and it's just going to take a little bit of practice. But let's go ahead and do a trig substitution. So thinking of the Pythagorean identities, maybe if I let my t be equal to some sort of trig function, I can use a Pythagorean identity to simplify what's inside the radical. So I kind of see that I have like a 25. What if I go ahead and let my t be equal to 25 minus, let's try like 5 cosine. I'm going to use a different variable, so I don't want to use t because that's already taken. So we're going to let t equal 5 cosine x. And then if t is 5 cosine x, what is dt? dt is going to be 5, derivative of cosine is negative sine. So it's going to be negative 5 sine t, negative 5 sine x. dx. Okay, so if I rewrite this integral, let's take a look at what it becomes. Okay, 4 is there. T cubed would be 125 cosine cubed x. dt would be negative 5 sine x dx. And then over square root of 25 minus 25 cosine squared x. Okay, so right away it's like, this integral became worse. But I want us to focus specifically on what's going on with the radical. We're going to see if it really actually got worse. If I factor out this 25 to the front, I have 1 minus cosine squared x. Okay, and notice that I can break the radical up, right? So I could break it into square root times square root. And the square root of 25 is 5. The square root of 1 minus cosine squared x, well, I can simplify the inside. 1 minus cosine squared x would be sine squared x, based on the Pythagorean identity. Okay, now the square root of sine squared x would be sine x. Okay, and we would have to pay attention to the quadrant that we're in to be careful when you're squaring something squared. It's not always clear whether it was positive or negative. But if your sign values are always positive, which it's kind of implied here, because it's an indefinite integral. It will be just make the sign x positive. Okay, and the other quadrant where sign would be positive would be quad 2. Yeah, quad 2. Okay, and then let's simplify the integrand now that we have that. So we have 4 over 5 And we have, sorry, there's also a 125, so we can pull that out and simplify that in a second. We have cosine cubed over sine x times negative 5 sine x dx. The negative 5 comes out. So we get 125 times 4, and that's negative, and then we have the sine x in the denominator as well as the numerator, so those will cancel. So that leaves us with cosine cubed x dx. Okay, so now this is going to bring us back to a previous integration technique, which we learned in a previous video, which is integrating using integrating using just trig, so trig integrals. We're looking at cosine cubed x, and I could view that as cosine x times cosine squared x. So this would be negative 500 integral of cosine squared x times cosine x dx, and then I could rewrite the cosine squared as 1 minus sine squared, which is nice because I can perform a u substitution. So my u, if I let my u be sine x, my du would be cosine x dx. And I can rewrite this integral as negative 500 times the integral of 1 minus u squared du. And I get negative 500 times u minus 1/3 u cubed. And reapplying the u back in, I get negative 500 sine x minus sine cubed x over 3. Okay, plus the integration constant. Okay, before I do the integration constant though, I want us to look back at where we came from. Okay, so what variable did we start with? It certainly wasn't an x. So we're not quite done with this problem yet. It looks like our original variable was t. So our last step will be we need to undo the we need to undo the x's basically. We need to put this in terms of t. So this is going to be the case anytime you do a substitution. Before you can be done, basically finding the antiderivative, you have to have the antiderivative in terms of the same variable as what you started with. Okay, so this is undoing our substitution. So if we went ahead and let t equal 5 cosine x, okay, okay, that means that t over 5 is equal to cosine x. Okay, so that gives me something that I can look at with a triangle, right? I need to figure out how to rewrite what sine x would be equal to. So if I look at a triangle that has x for my angle, and the cosine is adjacent over hypotenuse, adjacent would be t, and the hypotenuse would be 5, and I can use my Pythagorean identity to find that this side would be 25 minus t squared square root it. So then sine x, looking at my antiderivative, what am I trying to replace? I'm trying to replace all these sine x's. So that's why it's beneficial to me to write down, okay, what is that sine x actually equal to in terms of t? So then sine x would be equal to opposite over hypotenuse. So square root of 25 minus t squared over 5 is sine x. And then that allows me to rewrite the antiderivative with t's. This would be negative 500 times square root of 25 minus t squared over 5 minus square root 25 minus t squared over 3 and the numerator should be cubed. And then finally adding in the integration constant at the very end. The reason I didn't add that earlier when I almost did is because as you change the variables, technically your integration constant has to change as well. So if you wrote plus c earlier, then this would need to be technically a different constant, d, as you did your substitution, but it's such a minor detail that you can just wait until the end to write the integration constant. So that's the more simple approach to that. Okay, so let's look back and kind of get a handle on our full strategy here. So what we looked at in the beginning was an integral that we couldn't do a u substitution on. If we could do a u substitution, we wouldn't have done any of this, I assure you. Okay, so I saw a radical, I saw something hard inside, I couldn't do a u sub. So because there was something squared, the thought of using a Pythagorean identity to simplify the radical, namely in this step here, motivated me to try a trig sub. Okay, so a trig sub, looking at this trig identity, I kind of was in my head between, do I use the tangent secant or do I use the sine cosine? Well, this one I could see in my head, if I did sine cosine, it would simplify down to sine squared, which would be really nice. Okay, so thinking of that, it motivated me to use the cosine squared plus sine squared and do that substitution with cosine. So if I saw this expression and had used sine, we'd be okay. That would have been another way to do it. Tangent and secant, not so much. It wouldn't have been easy to simplify, and you would have hit a dead end there. Okay, and then we continued. We kept going, simplifying, just doing some algebra. We made it to a step where we needed to integrate right here, and in order to integrate, a u sub was able to help us. That gave us the antiderivative in terms of our change of variables. And then the last step is you have this variable that you used as a tool with their trig sub, and you need to get it back into your original variable. So that final step of taking it all the way back. And the right triangle will be involved here because we're always dealing with trig functions. Okay, so hopefully that kind of informs us of the strategy. Let's just keep working on some examples. Okay, so for example 2, we're going to take a look at computing the integral of 1 over b squared plus 16. So looking at my trig identities here, this one doesn't look like one where sine squared plus cosine squared equal to 1 is going to help, because I see I have the format b squared plus 16. You know, this kind of reminds me more of 1 plus tangent squared equals secant squared. So if I let my b equal to 4 tangent theta, let's see what it ends up being. Okay, my db would be 4, the derivative of tangent theta is secant squared theta. In this example, I'm using theta, which is a very common angle choice. So it's nice to get comfortable with using that as well. Okay, so the derivative of tangent is secant squared, and we can rewrite this integral as 1 over 16 tangent squared theta plus 16 db would be 4 secant squared theta and d theta. Don't forget that part. Okay, now simplifying the denominator, I can factor out a 16. Oh, and there's that Pythagorean identity that's popping out. That's nice. This is secant squared theta. So this is 1 over 16 secant squared theta. There's a 4 secant squared theta, d theta in the numerator. So the secant squared cancels, and leaving me with 4 over 16, which is 1/4. So I get theta over 4 for my antiderivative, but I'm going to look back to the original problem. Our original variable was b, so I don't want to stop at theta plus 4. I want to do my final step of the substitution. So recall that b, we let b be equal to 4 tangent theta. So that means that tangent theta is b over 4, solving that algebraically. So tangent of theta, opposite is b, adjacent is 4. That means the hypotenuse would be square root of 16 plus b squared from our Pythagorean identity. So then what is theta going to be equal to? Well, theta is just the angle. So theta, we can even see that here. If I took tangent inverse of both sides, theta would be equal to tangent inverse of b over 4. So I really didn't even need my right triangle in this case, but I don't regret doing it for you guys because it's still a good habit. Most of these you're going to need the right triangle to help with. So then theta is arctangent of b over 4. So we have 1/4 tangent inverse of b over 4 plus the integration constant. Okay, well, let's keep going, work on some more. This one's kind of interesting. Okay, so for our third example, we're going to compute the integral, the definite integral from 1 to 4 of the square root of x squared plus 4x minus 5 over x plus 2. Now, the first thing that jumps out to me is that with a quadratic that isn't a perfect square, good luck doing any sort of substitution if you don't literally see the derivative staring at you, which I do not. So in this case, we really have to complete the square on x squared plus 4x minus 5. I don't see a u sub, so it's pretty much the only step that I can take. I'm trying to write this in a way that helps me see my substitution. That is going to help me deal with the radical. So looking at this, completing the square, I'm going to leave, remember, half the middle term squared, take away, so half it, square it. There's still that minus 5. So this is going to be x plus 2 squared minus 9. Okay, I just did that in my head. It checks out. So I'm going to rewrite my integral with, this is square root of x plus 2 squared minus 9 over x plus 2 dx. Okay. This one has a lot of cool features to it, right? So I see an x plus 2 here and an x plus 2 here. And that's not too bad of a substitution to make. So I'm going to just say, you know what? It would be easier if that wasn't x plus 2 squared. It would be easier for just like x squared. So I'm going to let my u equal x plus 2. And my du would then be 1 dx. Okay, if my u changes, my limits change. The limits become 1 plus 2 and 4 plus 2. So rewriting my integral, I have the integral from 3 to 6 of square root u squared minus 9 over u du. Okay, why would I do that? Because when I take a look at inside the integral, I see something that is dangerously close to a Pythagorean identity. This one makes me think, This one, I would say sine and cosine, but notice that the variable term is the positive term, and it's going to get pretty hard here. If we try and go sine and cosine, you're going to get something that's going to have a negative. It won't quite work. This is the kind of expression that lends itself well to that identity here, where it's tangent squared equals secant squared minus 1. That identity, the right-hand side, looks a lot more like this. Okay, so I'm going to let my u equal, it's going to be 3 secant theta, because I'm trying to just get that clean tangent squared and then square root the tangent squared. It's kind of what my strategy is here. So my du would then be 3 times the derivative of secant is secant cotangent, or secant tangent, pardon. Okay, don't forget the d theta. So rewriting this, we need to change the limits again. Okay, so 3 secant 3 and then 3 secant 6 and then we get square root of 9 secant squared theta minus 9 over 3 secant theta times 3 secant theta tangent theta d theta. You can see right away some terms are going to clean up here. The 3 secant theta cancels. Simplifying what's inside the radical, this is equal to 9 times secant squared theta minus 1, which by the Pythagorean identity is tangent squared theta. So this becomes 3 tangent theta times that leftover tangent theta d theta. And I'm left with tangent squared theta d theta. And taking me back to my trig integrals, right? So looking at tangent squared theta and thinking about just how I would approach integrating that. In the interest of saving us a little bit of time, that ends up being tangent theta minus theta, evaluated from 3 secant 6 to 3 secant 3. Okay, and this is pretty hard to come up with an exact value here as is. If I tried to plug in tangent of 3 secant, like what? If I try and plug that in, what? So I'm thinking that probably the easier way of going about this would be I kind of backtrack on this one actually. Let's take a look at our triangle and see if that can give some guidance. Okay, so recall that we went ahead and let u equals 3 secant theta. So secant theta equals u over 3. So hypotenuse is u, adjacent is 3, and then this would be square root of u squared minus 9. So tangent theta is then equal to square root u squared minus 9 over 3. And theta then would be equal to secant inverse of u over 3. And then the reason I was pausing is because when we look at our limits for how this expression turned out, we can't really exactly compute tangent of 3 secant x. Like when I try and plug this in, I hit kind of a dead end. So frequently what happens is you kind of take a path and you're like, oh, okay, I was a little on autopilot. How about we don't do this step where we change the limits? We just kind of drop the limit step out. Okay, we're not doing this. We're not going to say that it's equal. We're not going to worry about these limits yet. Okay, so then once we rewrite our expression, 3 times square root u squared minus 9 over 3 minus secant inverse of u over 3, I can go ahead and evaluate that expression back with my u limits. So I kind of dodged the issue. My u limits were originally going to be 3 and 6. Okay, so I went back to this step where I last had u's. And because of how this problem worked out, that step's actually a little easier to evaluate the limits. So I'm kind of glad we had that moment of pause here to show you the thought process that goes into this. Okay, and that ends up being 3 root 3 minus pi, if you end up simplifying that. This is the end of this video covering the trig substitution integration technique. And in the next video, we're going to go ahead and take a look at how we do partial fraction decomposition to evaluate some integrals.